So our first topic is to talk about fluid properties. You'll see that we have a bunch of notes in here. Typically, I kind of deviate from those. And let's start that right now by deviating from them straight away. Phones. So anyway, let's see if this is this working? It's not working because it's not plugged in. That's a good reason. That should be working now, hopefully. So where are we? We are, oh, I guess I should have checked this last night, shouldn't I? So see how good, how's the lighting? Too bright, right? No. Tell me, too dark, right? How these work. That's probably great. All right. And so the notes are there as backup, and we'll move through these things at our own particular place. So this is fluid properties, I suppose. So the class is called Fluid Mechanics. And so the issues are, well, I think you know these things from your physics class. But the first question is, what is a fluid? Okay. So we very definitively use fluid, because fluid, of course, incorporates liquids and gases. And so if we look at the different materials we have, then you, I think, know the principal properties of these. So a fluid has a free surface. It takes up the volume of a container it's put in, but it always has an interface with a gas or a vapor at the top. A gas will fill completely the volume and expand to be able to do that. And fluids and gases will respond in the same way. As if you apply a force to a fluid or gas, it will give it a velocity. If you apply a force to a solid, by squeezing this, for instance, what it will do is it won't give it velocity, it will deform it, so it'll give it a displacement. So we don't talk about solids in this class in any particular way, but a solid would displace if you apply force to it. A fluid, if you applied a force, would give it a velocity, as would a gas. And the important properties that we deal with for these, I guess, would be density, or two important properties that we'll talk about today, and viscosity. We haven't defined either of these, but you'll certainly know what they are from your own life experiences. So the density of a fluid is quite high. Density of a gas is quite low. The density of a solid typically is high. It's just mass per unit volume. And the viscosity of a gas is relatively low, and of a fluid is relatively high, and it really doesn't really apply to a solid. Although things like ice, which we think of as solids, actually do creep and flow in some respects. So they also have some kind of viscosity attached to them as well. So that's kind of our basic ideas of what individual fluids might be. Perhaps my writing will get better as we go through this. So in our study of fluid mechanics, what we'll see is that we really want to quantify these behaviors. So you'll never see a question on a test, what is a fluid? Define a fluid. That's just not what we do. We want to be able to quantify properties in some, or quantify behavior in some appropriate way. And so the first way of doing that is if we look down through this list of things we'd like to achieve today. So I didn't really go through that. What is a fluid? Well, it includes liquids and gases. We'll talk, as your notes talk about, and in fact the first homework assignment is really on dimensional homogeneity, which we'll call it. And the rest of our discussions are on fluid properties of mass, weight, ideal gas law, compressibility, and wave speeds. But the next thing to talk about is dimensional homogeneity. And the easiest way to express that is it's a very important concept, because what it does is it allows you to be able to look at the expression that we'll use here And you can't necessarily say whether the expression is correct, but certainly you can say that the expression is incorrect if it doesn't satisfy this requirement of dimensional homogeneity. And so it's important that you keep all your units straight when you're doing your calculations. So let's talk about dimensions. So an easy example maybe is to look at something that's not really related to fluids, although it could be, I guess. It could be a droplet of rain. And that is to look at the equation for a sphere, very, very briefly. And so we know that the area of a sphere is equal to 4 pi r squared, right, where r is the radius. We know that the units of area, meters squared, length squared, and length squared here have to match on that, otherwise it's incorrect. And so we know at least this could be the correct equation because it actually satisfies dimensional homogeneity. If we want to calculate the volume of this sphere, how do we calculate that? Well, what we can do is we can take the area of that sphere and we can think of a very little sliver, perhaps I can draw this better here, is this little shell. Maybe I'm not drawing it very well. And this shell, can people see that, by the way? I have no idea. Even at the back, can you see this at the back, or is it too small? Can you hear me at the back? Can anyone hear me? Yes, some in the front. Okay. You take a small slither of this. It has some area dA, which we don't have to worry about because that's kind of incorporated in here. And so the volume is equal to the area of the surface multiplied by the thickness of this little shell, and we just integrate that from the center of the sphere to the outside. And so that looks something like this between these limits from 0 to A is the radius. And if we substitute this in here, then we end up with the integral, if we write it out, of 4 pi r squared dr between the limits of 0 and A, which if we do the integration is r squared dr is a third r cubed, so it's 4/3 pi r cubed evaluated between these limits, between 0 and A. And if you add the limits between them, then you end up with the volume should be equal to 4/3 pi A cubed minus 0 cubed, which is just A cubed, right? And so that's just an expression. Certainly you can all do that. But important in this is to realize that the units of this are now units of volume. And I'll typically use uppercase V with a line through it for volume in all we do. And the units on this side have also managed to say the same, that even though we've manipulated this, they should be units of volume. And so when we do that, we could also look at this, and we see here that we have units of length squared, and we have units of length. And so the main take-home story in this is we don't really care what these operators are that are used in here, the integration and the differential, because we just throw them away because they operate in some way on the units that are there. So irrespective of whether it's a differential equation or an integral or just a straight equation, we should always be able to match the fact that the units on the left-hand side of this and the right-hand side should be homogeneous. And that gives it a chance at least of being correct. Of course, many of you might be in petroleum engineering. Petroleum engineering is kind of an interesting discipline in that actually many of the equations that are used are not dimensionally homogeneous. And the reason for that is that typically they're unit specific. Every single equation we'll use in this class will be not unit specific. You can use whatever appropriate unit for that property in it. It doesn't have to be in feet or inches. You don't have to define that. But in petroleum engineering, many of the equations are you have to use viscosity in centipoise, you have to use lengths in feet, pressures in psi, and you get the outcome by a whole bunch of conversion factors in there in barrels per day or something. But everything that we do, we'll do in SI units primarily. In fact, most of your assignments should be, not all of them, but the vast majority of them will be in SI units. So dimensional homogeneity is an important part of what we do. So let's look at some other more interesting equations that perhaps relate to this class rather than the equations of a sphere. Certainly in your physics classes, you probably, I'm thinking, talked about Bernoulli's equation. And if you don't, we'll certainly talk about it in this. In this class, in common with the book, we use a right-hand coordinate system. So right-hand coordinate system means the thumb and first two fingers of your right hand, X, Y, Z. Z is always vertically upwards in everything we do. And relative to that, if we look at defining locations of this, this is a height. At this point, there is some kind of pressure, and it's moving at some velocity. No score through the velocity. Lowercase v is the streamline velocity. And you might recognize this equation. And it goes something like elevation plus pressure, P, divided by density and gravity, plus streamline velocity squared over 2g, plus, I'll put a term called viscous loss, which isn't in Bernoulli, but we'll add it anyway. And so for a fluid that doesn't have any viscosity, this expression is constant, whether you write it at this point, or at this point, or at this point, so long as it's along some streamline. And so we're not going to mess around with Bernoulli, but what we would like to do is play around with the units of this. So we know that the dimensions of this are units of length. So the dimensions of this have to be units of length. The dimensions of this have to be units of length because we're adding apples to apples. What we don't know, but what we could surmise from this, is that actually this is basically equal to force, that's F. A bracket on top of those is equal to mass times acceleration. So this term is actually the inertial term, the term that means that we have to provide a force to speed up the fluid in moving along this stream too. But that doesn't matter for now. But what we can do is we can take them in sequence and we can look at pairs of these variables. And maybe I'll do it over here. So if we look at these, and if, for instance, we know that this is units of length, we know this is units of length. So if, for instance, we divide this term through by this term, what do we get? We get pressure over density. So don't mistake pressures and densities for the symbols, times gravity. V squared over 2g. So get rid of this. We know that since this is units of length, this is units of length, you divide one by the other, it has no units. And if we look at this, then what we get out of it is something that looks like pressure divided by density and velocity squared. And so really, actually, just to make this clear, to show you what I've done, is I've just equated these two. Rho g is equal to v squared over 2g. So this just means I'm comparing units only. I'm only comparing units. I'm not actually equating those expressions. And this expression is called the Euler number. It's an important dimensional expression that we use in this class. You'll see it somewhere in the notes. If you look at the equation sheet that we have, when we talk about dimensional analysis, this here. So this is the Euler number here. We threw away the 2 because it doesn't matter. And what we do know is that it has no dimensions. So if you work out the dimensions for these different components, you'll find it has no units. And so it's an important number in what we do. Actually, it's the number that really tells you how much lift you get on a wing, for instance, or how much force or work you can get out of a turbine blade. So this is Euler number. So Euler is spelled E-U-L-E-R, after the Swedish physicist. If we look at these two numbers, do the same thing. So what we're going to do is we are going to divide this term by this term. So if we do that, we get the streamline velocity squared over 2g. And we divide it by this length, 1 over z. And I guess if we look at what the units of that are, we get v squared over, we don't care again about the fire in the building. And we can also manipulate this, so we end up with V over square root GZ. And this is called the Froude number after its originator. So the Euler number is the ratio of inertial forces to pressure forces. The Froude number is the ratio of velocity, inertial forces to gravity. And it turns out that this number here, which leads right into what we're doing today, it's the ratio of the flow velocity, which is V sub s, over the wave velocity. So we haven't proven that in any way, but this value on the bottom is actually the velocity of the celerity wave, where g is gravitational acceleration and z is the depth of the fluid, depth of water. So in other words, if you have a wave that sits on a surface, it sits on top of the ocean, then the depth of this is equal to z rather. Then the velocity of this wave, is equal to this celerity wave. And so we'll use that today in some of the things. So the point is you can go through these and look essentially at the dimensions. Also, if you're not really sure exactly what your dimensions are, you can calculate them from the other materials. So in other words, we said that the fundamental relationship you need for this class is what? No memory? So what are the units of forces? Well, we know that the units that we'll use in this class, we said we use SI. So we can divide them between only three groups. Those that relate to mass, which we'll call uppercase M. Those that relate to length, which we'll call L. And those that relate to time, which we'll call T, not surprisingly. And so in SI units anyway, the equivalent master units, if you like, for those, mass is the kilogram, length is the meter, and time is the second. Obviously you can use millimeters and centimeters, but the fundamental units that are used, that it's easiest to keep your mind wrapped around, is using these as standard units. And so, for instance, if you wanted to know what the units of force are, which it really isn't particularly obvious from this exactly what the units of force are, you can get the units of force because you know that force has to be equal to the product of mass and acceleration. And so if you know the units of mass, which are kilograms, but we'll use mass here, you know the units of acceleration are meters per second squared, so it's length per time squared. And so the units for this have to be ml t minus 2. And so you didn't need to know what force is, but you can get those directly just from knowing the quantities that you do know and substituting them in that. Likewise, when we talk about viscosity, you can work out what viscosity is from the fundamental relation which we give. Okay, so let's start on that. So we've talked about the wave speed. Let me get one thing started. I don't want to, well, let's not do that now. Let's carry on with something else. So if you look at the notes, what we've covered so far is we've talked about what fluids are. Don't really know what fluid mechanics are. We talked about a gas or a fluid. We've talked about physical quantities. We've done that. So that's why you should look at this stuff before you come to class. And we've talked about physical quantities. So one thing that we can do in putting this together is to make sure that we understand how to be able to make these transitions, to be able to figure out, in terms of our primary quantities that we use are mass, length, and time in the system that we'll primarily use. You can also do them in terms of force, length, and time, just a different system, but we'll tend to use this one. And from those, we should be able to define all of the properties that we'll use in this class in terms of the acceleration of the fluid, angular velocities, areas for length squared. We talked about densities or mass per unit volume. Energy, we can work out exactly what those are if we look at the rates of doing work, etc. And so those conversions, I think, are something that are probably already, hopefully, kind of ingrained in your mind. So the kinds of things that we talked about in terms of manipulating these things are included in a couple of examples here, which you can work through at your leisure to see. But I think you should all be on board with this in terms of manipulating expressions. If you know that this is volume per unit time, this is area, this is gravity, and this is length, you certainly should be able to put these things together and be able to make sure that the dimensions on two sides of an equation are congruent. And certainly if you look at things both including differentials and integrals, from what we've said, we can just throw these things away. We just don't care about them. You just have to balance the magnitudes of the individual components in there. So a very important, I think an important skill in what you're going to do in this class, and you should get your head a little bit around that. So what else should we talk about? We go back to this. So we've zipped through here. So we've said something about what a fluid is. We've said something about dimensional homogeneity and why it might be important in what we're doing. And so we've kind of assumed that you know something a little bit about fluid properties because we've used the word density and we've used the word viscosity as well already. But let's talk a little bit in more detail about what those important properties are. So mass and weight. Well, certainly you have it written here. So mass, our units are going to be kilograms because we'll use SI in preference. And so you know when you weigh something, you weigh it in either pounds or kilograms. We can also write this as the product of two quantities. If you take a density, so if you have something that has a particular volume, this is all very elementary, I'm sure, to you. But something that has a given volume, and it has a density rho, bless you, in kilograms per meter cubed, which is our standard unit. Then if you multiply that density by the volume, you end up with the mass in kilograms. So kilograms per meters cubed, well, I guess we don't need to do this, multiplied by meters cubed gives you just kilograms. So no surprises there. So the unit of mass that we'll use typically is kilograms. An alternate way of dealing with that is to write in terms of the weight. So mass is independent of whether you're on here or on Mars or any other planet in the solar system or beyond. But what is dependent on the gravitational field is the weight. And the weight is defined in terms of newtons. And specifically, the weight is equal to the mass, which we already know, times gravitational acceleration. And so it's a bad M, but you see exactly what it is. And of course, since we know the mass is also equal to density, is equal to density times volume, we can also include that in here as well. But the units of this, we can check also, are going to be kilograms. The units of acceleration are in meters per second squared. And so by definition, the unit of weight, if you like, in the SI system is the Newton, which actually happens to equal 1 Newton is the force required to give a mass of 1 kilogram an acceleration of 1 meter per second squared. So that you'll know that the definition of 1 Newton is 1 kilogram meter per second squared. So mass is the unit that allows us to be able to tell what kind of force is applied to something. And of course you can use that in a very simple sense to be able to, for instance, apply Newton's law, which is equal to mass times acceleration, which we can perhaps rewrite as this. An acceleration is a change in velocity with time, by definition. And so the force that has something is equal to the change in momentum. So we could also write this as the rate of change with time of mass times velocity. All I'm doing is taking this differential here and putting it out in front and making the point that If the mass doesn't change, then the only thing that's changing here is the velocity, and we should worry about that. So, a very simple exposition of that is if you throw a kilogram ball at me at 1 meter a second and it hits me in the chest, then it will apply a force as it decelerates from whatever the velocity is to zero velocity, and it will apply some force to me. So it'll hit me in the chest, and it will apply some force. So if it's moving at a velocity of 1 meter a second, and it's equal to 1 kilogram, then if we destroy that velocity over a certain amount of time, it will give a certain force. That force is applied to me. If that force is transferred to me, then it will try and move me at some velocity, the velocity of Derek, which is me, and it will move me at whatever mass I am, and the mass I'm about 220, so that's 100 kilograms. So just from looking at 1 meter per second per 1 kilogram, it's killed over some small amount of time. All of that momentum has to be transferred to me, so it's going to move me with some velocity, but I'm a much heavier weight. So it's going to move me at a velocity, and that has to be 100th of a meter a second to conserve mass. And so forces are the component that we work in. Gravity is the weight of this, which applies to it, which is applied to all of us, and which gives it the force that it applies that you have to react against. But it's exactly the same acceleration that is applied against something when you either accelerate it by throwing it or decelerate it by stopping it and transferring that force to you. So mass and weight are defined in those terms. Okay? So we've talked about units. We've talked about actually one other unit that's important to us before we move to this. I think I'm jumping around too much, right? Yeah, okay. I got it. So, yeah, so it's down here. Okay. So the other component that we're talking about, so unit weight, sometimes called specific weight, is a term that we'll call by gamma. And it's equal to density, product of density, and gravity. In other words, the term that gets used in this. So density and gravity and volume. So in other words, weight is equal to density times gravity times volume, from what we've seen before. This term here is specific weight. And so this is the important density, if you like, for a material, because it defines density not in terms of the weight in kilograms, which is dependent on the planet you're on, but determines the density, if you like, in terms of the force it will exert on you, which is independent of the planet that you sit on. And so the units of this would be newtons per meter cubed. And so, for example, water is equal to, what is it? 9.81 kilonewtons per meter cubed, which is also equal to 1,000 kilograms per meter cubed. Sorry for the running out of space. And the reason that they're related is that the unit weight is equal to the density of water times gravity, which is equal to 1,000 kilograms per meter cubed times 9.81 meters per second squared. So densities of water, important thing probably to tuck away in the back of your mind. Density of air, about a kilogram per cubic meter of that order, that allows us to be able to define those things. So coming back to the properties of fluids, then the behavior of fluids, say for water, of course water can exist, or CO2 for that matter, can exist in a variety of different forms. And so I think this is a graph of CO2. I'm pretty sure it's a graph of CO2 versus pressure and temperature. An important commodity these days because of greenhouse gas issues, of use in EOR recovery, enhanced oil recovery, to drive out, to lower surface tensions and to be able to get extra hydrocarbons out of the ground, the stuff that's going up our smokestacks. The behavior of CO2 in this particular case, like any component that can exist as a gas, a solid, and a liquid, is shown on a pressure versus temperature diagram. So in terms of our current temperature, what are we? In terms of Kelvin, we are something like 270 degrees. So we are something like, so 270 is here. The critical point for CO2 is something like 7 megapascals and 30 degrees centigrade. So 30 degrees centigrade is definitely essentially 300 Kelvin. So that's exactly this point here. 7 megapascals is equal to 70 atmospheres. So on a log scale, this is equal to 70 bars, this point here. Doesn't matter about that particularly. But the point is, if we sit within a gas and we cool it, then what will happen is that we'll change from being a gas as we go along this trajectory, potentially to being first a liquid CO2 in a gas cylinder. And then as we chill it even more, it'll become solid CO2, dry ice that you drop in water and you get smoke coming from it. And so on some trajectories, you'll go through gas to liquid to solid. But below the triple point is where a liquid and a solid and a gas are all kind of coexisting at roughly the same point. If you make that trajectory below the triple point, what you'll do is you'll go directly from a gas, you'll sublimate, transfer directly from a gas into a solid without first going through a liquid. And so likewise, gases are typically, we've said this before, gases are relatively low density and low viscosity. Liquids have relatively higher densities and higher viscosities. And so the interesting thing about a supercritical fluid is that the essential behavior of a supercritical fluid is that it has basically the density of a liquid, so it has a high density, but it has the viscosity of a gas. So it gets these two preferred quantities. And the desire of this is that if you want to be able to stick this in the ground instead of putting it up into the atmosphere, you want the fluid to have a high density because you want to not fill up all of the available aquifer or reservoir space you have. And also you don't want to have to provide a lot of power to be able to push it against viscosity as you push it into the pore space in underground reservoirs. And so the way that CO2 is thought about being put into the ground is in this particular state where it has supercritical properties, which is hotter than 30 degrees centigrade, it's not very hot, and higher pressure than 70 atmospheres, which isn't very high either, in which case it has actually relatively desirable properties compared to a gas, which would take up too much space, and a liquid, which you'd have to provide too much energy to be able to push it into the pore space of the porous medium. So anyway, so that's the basics of our behaviors. So we're kind of down to here is where I'd say. So we haven't really used the notes, but we've kind of drawn on them. So let's talk about equations of state. So we have equations of state for two different components that we're dealing with. We're talking about fluid mechanics, and fluids come in two different varieties. They come as liquids and they come as gases. And so it shouldn't come to some surprise that the equations of state that we use for them to represent their behavior are defined in terms of a gas law and also the behavior of a relatively incompressible fluid, which is a liquid. So let's look at the, gone through this, we've talked about units, you all know degrees Kelvin and Celsius, what they're related to, I've assumed that. Now you should know how to convert into Fahrenheit and Rankine, which are the equivalents. But let's talk about, slow down a little bit and talk about the behavior first of gases. And so in the properties that we've talked about, you've certainly come across the ideal gas law in your past. Although we don't really talk very much about compressible liquids in this class, we do need to know about at least the equations of state to be able to look at static fluids. And not all liquids are ideal. Ideal means that the pressure that's applied in a fluid is directly related to its density, the gas constant for that fluid, and also the temperature that you find yourself at. So you'll certainly have seen that before. You should remember, of course, that both pressure and temperature are absolute. So the temperature is relative to 0 degrees Kelvin and has to be in Kelvin, in the SI units or Rankine. And the pressure is relative to absolute zero pressure. In other words, not the pressure we find ourselves at now. And so this is zero pressure, bless you. And if you look at current pressure, then atmospheric pressure is equal to 0.1 MPa, which is equal to 1 bar. And so this is abs pressure. This is what we'll refer to as gauge pressure, G-U-A-G-E pressure. Right? And so right now we think the pressure is 0, but actually it's not, and it's because we have a whole bunch of air sitting on top of us, and the weight of that air gives us a pressure of 1 atmosphere, one bar. And in SI units, that's equal to 0.1 MPa, or if you prefer the same in kilopascals, is 100 kilopascals. So these are equivalent to each other. And so when you deal with pressures, we have to deal with them in this form. Absolute pressure, absolute temperature, and this, of course, is the gas constant. And this, of course, would be for gas I. So this would be the gas constant for gas I and the density for gas I, whatever that might be. If you want to define it in terms of a universal law, I'm not sure. So I think I'm going to slow down on the numbers of windows. So ideal pressure equals density times gas constant times absolute temperature. This is the pressure in this gas, this is the gas constant for this gas, and this is the density of this gas. We can also rewrite that by substituting in for this gas-dependent gas constant, a universal gas constant, which we call R bar, and the atomic mass, if you like, of the substance. So this is equal to the universal gas constant. I left out an I. And it's the molar weight. Yes. And in that particular case, then the pressure in any particular gas, all I'm going to do is substitute this into this equation, is the density of that particular gas multiplied by this universal number divided by the molar weight of this gas and the temperature. So you can use it in either form. So this is perhaps more convenient because now this is a single number which doesn't change with the gas that you're dealing with, but you have to use the molar mass of that particular gas, whatever it is, 16 or 12, in a consistent set of units. And of course, if you're using kilograms per meters cubed for this, then this should be in per kilogram. So it's usually given as grams for a mole of material. So you take the molar mass and divide by 1,000 grams per kilogram to give it in molar mass Yep. This one here, molar weight of gas. Sorry. I abbreviate things. WT is weight. Sorry. So yeah, do shout. Yep.
What's the subscript on the right? Is it
I. Lowercase I. Yeah. This is. Okay. Yeah. Criticism accepted. So when I do things, I'll say in advance that the rows and P's start to look similar, right? P row. My Z's and times look similar. And I'm trying to think what else also looks similar. Can't think. There are others. So be aware of those. Okay? So what this does is allows us to be able to calculate the pressure, the density, say, of a gas given a pressure and a particular temperature at which you find yourself. Any other questions coming up? And so we can look at behavior in two different ways if we compress gases. We compress gases for lots of reasons. Compress gases like CO2 to stick it in the ground for EOR or for sequestration. We compress them to put natural gas in pipelines, for instance. Gases get compressed in internal combustion engines by the motion of the pistons and then combusted and exploded, detonated, I suppose, right, to be able to do it. But if we take a given volume and we change the volume that includes that gas, then what we can do is we can then look at the pressures that develop as a result of that. We know that the density here we could write as what? We know that density is units of, we can write it as the mass of the gas in that container divided by the volume, right? That's nothing other than this term here. And we can also write, we can use this non-universal law here, doesn't really matter. And so what we can look at in this is that what's changing in this is that there is no change in mass that's occurring. And so we can look at the product of this times volume is equal to mass times R times T. And so we keep the same stuff in the volume, right? So you put some gasoline in an internal combustion engine, it goes in the cylinder, you compress that material, nothing's coming out, so you always have the same amount of gasoline or gasoline vapor in there, so the mass doesn't change. And so we're not allowing anything to escape, so that would be the case here. And so, whoops, didn't mean to do that. And so if we know that this behavior, in this particular case, is constant if we compress something, and we, for instance, don't allow the temperature to change as we compress it. So we know that for isothermal compression, the pressure times the velocity at state 1, maybe in this big cylinder, should equal the compression in the state where it's scooted down times velocity at the second stage. And so if we, for instance, know what the pressure is initially, we know what the initial volume is, and we change the volume, then we can calculate the remaining fluid pressure that we have within the system. In the same way, we can also look if we don't change temperature in this particular case. In other words, if the gas constant, which is a constant, and the temperature don't change, then we can also look at these being equal to some constant magnitude, which is this expression here. But we have to look at it in two different ways, isothermally and isentropically. And the relationships that we get are slightly different in each case. Isothermally means that we take our bicycle pump, if you still use bicycle pumps, put your thumb over the end and you push down on it. You'll feel your hand get warm because you're doing work on the gas that's in there, the fluids that's in there. And if you allow that fluid to dissipate into the surroundings so the temperature of the gas in there is no longer increased, then that's an isothermal system because you're allowing all of the thermal energy to dissipate. There's no change in temperature in the long run that occurs with this. And so you should be able to calculate the magnitudes of the fluid pressures or the fluid pressures in this particular case. You start off with the pump with volume 1, has atmospheric pressure in it. Put your thumb on the end, you change the volume of the pump, it has a new pressure in it, you can calculate it by using this expression. Getting there, don't worry. If you do it isentropically, isentropically means you take the same pump and perhaps you put your thumb over it and you pump it down, but it's completely insulated by doing it in a vat of plastic packing peanuts. So none of the entropy, none of the energy can get out of it. And so all of the thermal energy that you develop by the work gets trapped in there. If you do that, then the equivalent relationship, instead of being this, is just one that includes an extra coefficient in it, which is this magnitude of the ratio of specific heats. It's a thermodynamic quantity. It doesn't matter how we get it, but it's something of the order of, for air, it's about 1.4. It's a constant ratio of this. And it's a term that we can use. And so that's useful for us because we can use the ideal gas law to be able to, for instance, see how pressures change if you pump liquids into a closed volume, or if you change the volume of that particular control volume, which we'll use later on when we talk about different systems. But we can also use it to be able to say something about things like the compressibility of a fluid. And so we know that a gas, one of the properties we didn't mention about a gas is that if you compress a gas, it's easily compressible. You get a balloon and you can compress it. Well, if you don't burst the balloon, you can certainly compress it. If you compress the liquid, it's actually very incompressible. It's actually the modulus or the stiffness of water is about the same as stiffness of rock in the ground. It's just that it kind of squidges out. And so the other property that we can define that describes the behavior of fluids is modulus. This is modulus, which just by definition is a change in pressure that you get with a change in volume, a relative change in volume. So you have a volume that is V0. You change it by some amount, say 10% would give you a dV over V0 of 0.1. 1 cubic meter, you reduce it by 0.1 of a meter. That's a volume strain, if you like, of 0.1. 0.1 divided by 1 is 0.1. And you get a change in pressure that results from that. You compress it, and the pressure goes up. And so the volume change, if you compress it, is a reduction in volume, but the pressure goes up. And so there's a negative sign put here. So this coefficient is equal to a positive number. So the volume goes down, but the pressure goes up. So you have a negative over a positive. Multiply that by a negative, and you get a positive out of it. You can also define it in terms of a change in density over the original density of the fluid, in which case this is a positive value. You change the fluid pressure, the density goes up. Numerator is positive, denominator is positive, and so you don't have to apply this change. And so the other thing that we can also do with this is we can use this to say something about the stiffness of a material. So we can use the ideal gas law for gases to be able to take that. So we know that this is true from what we've already said, right? If we differentiate this, we get the change in pressure with density is just equal to dP d rho is just equal to the differential of this, which just disappears, and you're left with a constant. You do that differentiation. If you take this definition and you throw it into here, which is what we're doing here, then you find out that you get the modulus, if you like, defined as this constant, which we know, multiplied by the density. If you then rewrite this expression in terms of this, and you substitute for this value here into this expression, then you basically cancel out the two constants, and you end up with a very surprising result, which basically says that the stiffness of a gas is equal to its pressure. So in other words, we know that we're sitting here at 1 atmosphere here. The room's filled with air. And so if I take a balloon full of air and I try and compress it, I know that the stiffness of that air is equal to 1 atmosphere, which is equal to 0.1 MPa, megapascals. which I haven't defined, but it's also MPa, if you didn't ask, is mega newtons per meter squared. And so that may seem very esoteric, but it's not, because actually the way that I'm communicating with you, hopefully communicating with you audibly, is transferred by the acoustic speed of sound in air. And the acoustic speed of sound in air, as we'll see next time, as indeed related to, for instance, things like tsunami waves, which we'll talk about next time, is transmitted by the stiffness. So we'll leave it there.